All right, everybody, let's get started. All right, so good afternoon, everybody. Today we are going to explore building a microchip for cryptocurrency. A microchip that can do the same thing as your software node, but is faster, more reliable, uses less energy, and can be built for a fraction of the cost. This hardware approach has already paid off for Bitcoin mining. Satoshi mined the first Bitcoin with his CPU on January 3rd, 2009. Shortly afterwards, people realized they could mine faster and earn more profit programming a GPU to do the mining instead. Later still, innovative people figured out how to make an electrical circuit for mining and etched that circuit onto a tiny silicon die. The era of the ASIC miner was born. And every year still, mining companies come out with new, faster, lower power, and cheaper mining rigs as they compete to find the next block. The efficiency of the technology increased tremendously too. Satoshi's Intel i7 could do about 100,000 hashes for every joule of energy consumed. The first GPUs could do about 1.2 million hashes per joule of energy, and the first early ASIC miners could do about 500 million hashes. The best ASIC miners today can do about 60 billion hashes for that same joule of energy. So there's been a 600,000 time improvement in the technology since 2009. But the network capacity in transactions per second has flatlined. It's been 7 transactions today, 7 transactions per second a decade ago, 7 transactions per second in the days of Satoshi. If transactions per second had improved in lockstep with the progress in mining chips, we'd be at 4.2 million transactions per second today. So why aren't miners supporting the network? Why aren't they building better, faster nodes that allow us to actually scale? It's obvious that Satoshi wanted them to. I think the answer is nuanced. I think proof of work was the right idea, but the Satoshi picked the wrong hash function. Rather than dumb hashing, he should have picked a hash function such that a miner's hash rate was equal to the rate at which that miner could validate transactions. If so, the massive improvements we've seen in mining technology would have been coupled to equally impressive improvements in Bitcoin full node technology. This brings me to my role at Nexa. While Andrew Stone leads a top-down effort building off of the Satoshi codebase, I lead a bottom-up effort implementing what Satoshi described in the white paper directly in hardware. I'm not writing any software or even using a CPU. Instead, I'm building a node as a circuit of digital logic gates. Our hope is that when these two arrows converge, that we have achieved our goal of building a better Bitcoin. To continue with this talk, we need to do a quick review of the building blocks of digital logic. The most important component is this. It's a wire, and its behavior is so simple that it's beyond the grasp of many software developers. If I apply 0 volts here at the input, I get 0 at the output. If I apply 1 volt at the input, I get 1 volt at the output. You can model this behavior in Python as shown. It's a while loop that's always mapping the input to the output. In Python, it takes several hundred clock cycles for the input signal to propagate to the output. How long does it take in the hardware case? Now, this is the part that stumps the software guys. they might answer that with a lot of work, it could be as fast as 1 clock cycle. But that's totally wrong. It takes no work at all, and the signal propagates at the speed of light. It's literally just a wire. And this is part of why hardware can be so fast. You get this built-in while loop for free. So this is a NOT gate. If the input is 0, the output is 1, and vice versa. Next is an AND gate. The output is 1 if all of the inputs are 1. Then we have an OR gate. Then we have a multiplexer. A multiplexer is like a switch. And lastly, we have a flip-flop. Flip-flops are used to store state, to store memory. And the way it works is the input gets saved to the output when the clock goes from 0 to a 1. Together, these gates form a Turing complete set. And what that means is that any computation that can be performed by a suitable combination made of these 6 components. Another way to look at this is that you could solder together your own Turing machine made with only those 6 building blocks. Bits versus symbols. A wire carries a single bit. A flip-flop stores a single bit. A bus is a collection of wires and carries a bunch of bits that we call a symbol. Symbols are saved in registers, and registers are just flip-flops side by side. Now let's get started building our Bitcoin hardware, or our hardware node, or Nexa and Bitcoin hardware node. We start with an abstract description of our validation engine. The node consists of a tape of squares, and on each square a symbol may be written. The read-write head can inspect the symbol on the square in front of it, and optionally can overwrite it. It can also splice a new square into the tape. Lastly, it can request information from the UTXO database. That's basically it. That's our validation engine. With that out of the way, what are our goals for our hardware node? What properties do we want our better Bitcoin to have? Well, my answer is that we want it to be scalable, compressible, extensible, and incentive compatible. What I mean by scalable is that it must be pipelinable, parallelizable, and the work to validate a transaction must grow very slowly with the network size. When I say pipelinable, I mean we can validate transactions with that tape only moving in the forward direction. By parallelizable, I mean we can have parallel validation and pipelines operating together in parallel. Bitcoin already has this last property here. By compressible, I mean 2 things. We need a way to show that a coin exists with a small compact proof, and we need a way to show that a coin is unspent with a separate compact proof. Bitcoin already has this first property. It's the Merkel branch proof in the SPV section of the white paper, but it doesn't have the second. By extensible, I mean that our validation engine can emulate a Turing machine. If it can emulate a Turing machine, then it can be extended to perform any possible script with a suitable extension to just a circuit inside the head. And that's a very localized change. And I've already talked at length about how I want the hash per second mining to be coupled directly to do the transactions per second validating, which is what I mean by incentive compatible. It turns out that we can fix Satoshi's Bitcoin and make it check all of those boxes with only 3 simple changes. The first is that we have to calculate the root hash for a block using a compact bitwise prefix tree rather than a Merkel tree. This builds on Amari Sachet's idea to hash the block as a set rather than as a list. This change makes it scalable. Strangely, it also turns our validation engine into a Turing machine and thus makes it extensible. The second change is to store the UTXO set in a compact bitwise prefix tree and commit to the tree's root hash in the block header. This builds on ideas from the ultimate blockchain compression thread on Bitcoin Talk in 2012. This change makes it compressible. It makes it possible to prove that a coin is unspent with a compact proof. And lastly, I want to use a hash function that forces a miner to exercise the entire transaction validation pipeline for the reasons that I've already mentioned. Now let's zoom into the wire and gate level. I implemented the tape using a bunch of wires, a bus, and I connected those wires to the head so I can read and write the symbols. So the bus is coming in here, and that's a symbol seen by the head. There's also a wire for every symbol that lets our head know how to interpret the symbol it sees. Is it a pub key? Is it a signature? Now, the clock rate is about 100 megahertz, which means that 100 million symbols are flying past the head every second. But sometimes the head might need longer than 10 nanoseconds to perform its operation on the square in front of it. For example, it takes about 20 microseconds in hardware to verify a digital signature. For this reason, I needed to add these two control wires here. These wires implement hardware flow control. To get more time, the head asserts the full wire, which tells the upstream process not to send any more symbols. This flow control signal propagates in a few dozen picoseconds, less than a clock period, so the bus stops instantly. When the head is done verifying the signature, it can release the flow control lines to restart the flow of symbols. Now, it's not possible to achieve sub-nanosecond flow control like this in software. Now let's get our validation engine to process a transaction. Here is a diagram from Satoshi's white paper that explains how it works. Alice's transaction that pays Bob contains, well, the TX ID of the coin she's going to spend, Bob's pub key, who she's sending the coin to, and her signature that authorizes the transaction. But in order to process this transaction, our node needs to know a little bit more information. It also needs to know Alice's pub key and this thing called a signing hash. So here's how we process this transaction in hardware. First, the head sees the ID of the coin being spent, and it saves a copy of that symbol into an internal register. It also looks to see if the coin exists in the UTXO data space and is unspent. If it is unspent, the head saves Alice's pub key into an internal register and also splices the pub key into the tape here. The next symbol passes by, which is Bob's pub key, which gets saved into this register here. Now there's enough information to compute the signing hash. The circuit automatically performs this hash because this is fixed dedicated hardware. So what happens almost instantly, and it splices that hash back into the tape. The next square that passes is the signature of Alice, and now we have enough information to verify the transaction. The hardwired verify module, this module here is just a bunch of different transistors. It verifies the transaction very quickly. And if it's valid, it marks that symbol on the tape as valid, and it also pushes what is now Bob's coin into the UTXO set, and we're done. So I've demonstrated that transactions can be validated with the tape only moving in the forward direction, which means I get to check the pipelinable box. Let's look into parallelizability next. In this diagram, I've added a second validation pipeline in parallel to the first. There is a switch which routes transactions to whichever pipeline is not busy. The first problem we encounter is that both heads, head 1 and head 2, must access the same UTXO set. If pipeline 1 spends a coin, the coin must be spent from the perspective of pipeline 2 as well. But what if both pipelines attempt to spend the same coin on the same clock cycle? This is a race condition that we must prevent. It's really easy to prevent this in hardware though. What we do is we invert the clock signal to pipeline 2 so that it's physically impossible for the two heads to access the same coin at the same time. Either pipeline 1 grabs the coin on the clock's rising edge, or pipeline 2 grabs the coin on the clock's falling edge. The other problem we encounter is that the transactions might come out in a different order than they went in. For example, TX2 might come out and enter our block candidate before TX1. If our node solves the block, its peer might reassemble this block in a different order, calculate a different root hash, and thus reject the block as invalid. Of course, this can be fixed by sorting the block, but sorting is not pipelinable as the tape must move forwards and backwards. So we don't want to sort because sorting doesn't scale. If we interpret the white paper literally, Bitcoin is either parallelizable or pipelinable, but it cannot be both. Now, I don't think Satoshi literally meant a Merkel tree. I think he meant a binary tree that would work for SPV proofs. The problem is that a Merkel tree is for lists. What Satoshi really wanted was a tree for sets. A tree with this property is the compact bitwise prefix tree. It still works for SPV proofs, but it also produces the same root hash regardless of the order of the transactions in the block. As long as the two sets of transactions are equal, the root hashes will also be equal. If we use the prefix tree, we can eliminate the need for sorting and recover the pipelinable property. With this one change, our cryptocurrency becomes scalable. So I get to check the parallelizable box, which flips the AND gate to true, and thus our coin is now scalable. So why is pipelinability and parallelizability such a big deal? With pipelinability, we can guarantee that our throughput in transactions per second can be as fast as the reciprocal of the slowest step in the pipeline, which will typically be signature validation. The other shorter latencies don't matter at all. With parallelizability, our throughput can be multiplied by the number of parallel pipelines. Thus, we have a system that scales arbitrarily just by increasing the pipeline depth and the number of parallel validation engines. Basically, we can get to any scale we want just by throwing more hardware at the problem. Okay, I mentioned earlier how this change strangely also gave us a Turing machine. Let's dig in deeper to see how. Consider the case where Alice pays Bob, and then Bob immediately pays that same coin to Carol. Remember, we can't control the order. So the payment from Bob to Carol in the blue box there, it might get checked by head one before the payment from Alice to Bob is registered. So when head one looks up Bob's coin from the UTXO set, it's not going to find it. But nor will it find proof that the coin was already spent. So this transaction cannot be marked valid, but it cannot be marked invalid either. It's undecided. To deal with undecided transactions, we have to add a third pipeline that feeds those transactions back into the input. When this transaction re-enters pipeline 1, Bob's coin is now sitting in the UTXO set because head 2 put it there, and the transaction can be validated normally, and everything works out. So it is the fact that a transaction can remain undecided that makes the feedback path necessary, and it is the feedback path that allows the machine to emulate a Turing machine. And this is really easy to see. So from the perspective of the head, the tape is doing loops in front of it. But from the perspective of the tape, the head is walking to the end and then starting over at the beginning. But remember, the head has control over the flow control lines, so it can stop the tape at any square it wants. So what it really looks like is this. The head can move both right and left on the tape, and we already showed how the head could insert new squares into the tape, so the length of the tape is effectively unbounded. And as many of you probably know, this is all we need to show that our validation engine can emulate a Turing machine. I need another 25-minute slot to talk about all the amazing possibilities this opens up. But I'll say that with this architecture, we can add things like quantum-resistant signature schemes purely in script without even requiring a hard fork or a soft fork. So now we get to tick this box. Our coin is now extensible. The next step is to make it compressible. Currently, full validating nodes use their UTXO set to determine whether a coin exists and is unspent. That's it. But they could get that unspent status from a compact proof if such a proof existed. You see, we could easily make this happen. The way it would work is that miners would store the UTXO set in a compact bitwise prefix tree and include the tree's root hash in the block header right beside where they're including the root hash for the block. Full nodes can now check that a coin is unspent with only a branch proof to the block header. There is no longer a need for full validating nodes to maintain a UTXO database. Calculating the UTXO root hash is not hard for the miners. It is pipelinable, parallelizable, and has O log S complexity per insertion deletion, and so it meets our definition for scalable. So I've shown how we can add compact proofs that a coin is unspent, which means I get to tick this box here, and the AND gate fires, and our coin is now compressible. We're on to the last step, and that is the hardest one, because we need to make our own ASIC. So this is an artist rendering of the Nexa POW ASIC. It's just a 10 by 10 millimeter ball grid array that looks like any other microchip. But inside is a Bitcoin full node core that can process 1 million transactions per second. It also supports Nexa's extended instruction set, so it can do the useful things with script that Andrew Stone discussed this morning. It has 32 parallel transaction validation pipelines, 32 elliptic curve point multipliers for fast signature verification. It has integrated mining cores and a massively parallelized tree root hashing circuit. And in total, it contains about 360 million transistors. That seems like a lot, but some GPUs now have 100 billion transistors, so this is by no means a big chip. TSMC is the big semiconductor fab in Taiwan, and their 16 nanometer process can place about 40 million transistors per square millimeter of silicon. So the die inside this chip will be a 3 millimeter square. So that's something that could easily fit on the tip of your finger, or you can maybe even balance it on the head of a pin. The Nexa POW algorithm, which is implemented inside this chip, involves verifying a digital signature and updating the UTXO set, which are the two bottlenecks of full node scaling. To mine, the chip uses the exact same pipeline as it does to validate transactions, so mining and transaction validation are truly coupled one-to-one. So now we get to tick the last box here and achieve the vision of a better Bitcoin. Our ASICs won't be ready until at least 2026 at the earliest, but there's still a lot of useful things we can do directly in hardware in the meantime. This is Node by Nexa. It's a small hardware-accelerated cryptocurrency full node. It's this big right here. It has a network connector. It has a network connector for connecting to the internet. It has a memory card slot where the blockchain gets stored. It has a little toggle switch for changing between mainnet and testnet, and it has a USB port for debugging, for development, for loading new bit streams onto the FPGA. The heart of the node is the Nexa system on chip. This system on chip contains a quad-core RISC-V processor running at 1 gigahertz, which boots into Linux. But the idea is not to actually use Linux for the full node. We want to get to the point where the full node exists purely in hardware, so transactions come in over the network, are routed through our hardware, through those transaction pipelines, and solve blocks are written directly to the memory card without any intervention by the operating system. This way, the data pipelines remain purely in the hardware domain, where they are very fast. From the Linux perspective, the hardware node is a device in the Linux device tree. Wallet software running on the Linux side could talk to the hardware node to get updates on balances, for example, or to broadcast transactions into the network. So this truly is a cryptocurrency computer. Nexa versus Ethereum. People ask me, what is the difference between Nexa and Ethereum, or even Bitcoin and Ethereum? Both have flexible scripting systems, but the underlying architecture is very different. Nexa uses the same UTXO model as Bitcoin. There are no accounts. There are only coins, and coins can either be spent in full or not at all. A typical transaction looks like this. There's the inputs being consumed, the signatures which authorize the spending of those inputs, and the new outputs being created. And if this transaction succeeds, these coins are removed from the state, and these 3 coins are added. So either the whole transaction goes through, or none of it does. So this architecture is nice because the changes to the global state are localized to the specified inputs of the transaction. And it's this localization which allows for the high degree of parallelism, which I discussed earlier in my talk. we can have multiple heads checking multiple transactions, and there will be no conflicts because we know ahead of time the region of state space that each transaction can modify. So the UTXO model is highly scalable because it is highly parallelizable. Ethereum is very different because it uses an account-based model. You can imagine the head is inside the global state space and has read and write access to everything. This makes Ethereum more flexible, but can also lead to unexpected results. For example, Alice could write a transaction that debits her account and credits Bob's account. But maybe, if the contracts are confusing, as they often are, Eve can write a transaction that debits Alice's account and credits Eve's account. This is not possible in Bix or Nexa because the inputs are essentially firewalled. If you've understood my talk, you can probably see that Ethereum's model won't be parallelizable like the Bitcoin or Nexa model because the region of state space that a transaction can interact with cannot be localized like it can in Bitcoin. So this is my last slide. I think I'm going to go 20 seconds over. But I'm not saying that Nexa is better than Ethereum. Instead, they are two completely different things that serve two different purposes. Here's how I look at it. In Nexa, miners compete via proof of work to confirm recent transactions in a block. The global state access is not necessary because a coin belongs to its owner. Bitcoin Next is the chunk of a digital commodity. Ethereum is different. In Ethereum, shareholders vote via proof of stake on which global state changes to permit. Global state access is necessary to execute shareholder resolutions, which could be anything. Ether is a share in a decentralized company. It is not a coin or a commodity like Bitcoin or Nexa. And that's my talk. Thank you for listening. Any questions? Yes. You want to come at me?
Thank you for the presentation. It's very good. And if a miner want to mine the Lexus, do they need to boot the FPGA or the circuit to do that, or they can still using their own hardware?
So we're still in the process. Like right now, the mining algorithm next is a bit different than what I talked about. So this will be after a hard fork, but the algorithm will be completely open source. So we will be coming out with our own ASIC that we will very likely make available. But other people will be able to build ASICs too, because it'll be a totally open source algorithm. And that's what we want, because we want people to be able to compete in a free market. Because if people can mine Nexa better than I can, well, that makes the whole network better. So that's exactly what we want to achieve.
The 30 instruction set, but how implemented in the hardware?
Yes, that's right. So we specify the protocol, and we will create a reference implementation, but anybody's free to optimize on that. And that's what we want. We want to create a dynamic environment to reproduce what happened in Bitcoin mining, because that was an amazing result. Bitcoin mining, the hash power grew by 1,000 trillion times. So we want to make that happen for no technology to make Satoshi's vision a reality and have peer-to-peer electronic cash for the entire world. Well, thank you. Thank you.